Okay, in this question, it's giving us some data for this reaction at 660 Kelvin. And this is a experimental data, reactant concentration, so that's the NO and the oxygen, and then the rate of disappearance of NO. Okay, so that's the rate that this NO is disappearing. Okay, that will be an important point. We'll see in a little bit. Okay, first it says determine the order of the reaction for each reactant. Okay, these are the two reactants. What is the order of the reaction? Okay, so here we see, all right, I'm holding the oxygen constant and the NO I'm doubling. All right, what happens to the rate? Well, it goes from say 25 to 100, right? So it quadruples. Okay, so that means the order of reaction with respect to NO is 2. All right, so we could say the rate is equal to K times NO squared, and then we're going to have another factor there on the oxygen, O2 to the, so if we hold NO constant, okay, and double the oxygen, the rate doubles. Okay, so a doubling of that rate would be just the first order. So this would be the rate law, second order in NO, first order in oxygen. Okay, write the rate equation for that reaction. There it is. Calculate the rate constant. Okay, in order to calculate the constant, I need to know a rate and the concentrations. Okay, so I can put in any one of these combinations and I will get the same results. Okay, so to make the calculation easy, I am going to use the I'm going to go ahead and use this one, first line there. And if I have 0.01 for each of these, that's going to be 0.01 squared times 0.01. All right, that's the reactants. And then the rate, and this is where we have to make a distinction, okay? Because this is the rate of the reaction, okay? Whereas this is not the rate of reaction, but the rate of disappearance of NO, okay? Now, the difference is that you will recall in our discussion of the rate of reaction is equal to the change in concentration of whatever reactant I have per unit time, okay? But in order to make it the rate of reaction instead of the rate of disappearance, and since that would be a reactant, I'd have a negative there to make the sign positive. But instead of being a rate of disappearance, I need to divide it by the coefficient. Okay, so if my coefficient were A, I'd divide that by A, and that gives me the rate of reaction. So the rate of reaction is equivalent to the rate of disappearance of the reactant or appearance of the product as long as we divide it by the coefficient. Okay, so that's the only difference there. So our rate, instead of being 2.5 times 10 to the minus 5, is going to be 1.25 times 10 to the minus, what's that going to be? Minus, yeah, still minus 5. Okay. All right. So if we do that, 0.01 times 0.01 is, I mean, this is 10 to the minus 2, so that'd be 10 to the minus 4, and then another 2 would be 10 to the minus 6. Okay, and I missed my k in there. Okay, so k times 10 to the minus 6, we can divide that, and if we divide this by 10 to the minus 6, then this will end up being 12.5. Okay, and I believe we can go ahead and just round that up to two significant figures, and our k is equal to 13. Okay. Let's see, were there any other questions for that one? Yes. Calculate the rate in moles per liter per second at the instant when NO is 0.015 moles per liter and O2 is 0.005 moles per liter. Okay, so now that we have our rate constant, we know the rate is equal to 13 times the concentration of NO squared times the concentration of O2. Okay, so we want to find the rate. So we put in 13 times 0.015 squared times 0.0050, and that will be just like that. And if we calculate that out, we have, let's see here, we have 13 times 0.015 squared, okay, times 0.005. And what we end up with, 1.46 times 10 to the minus 5. Okay, and we should really call this 1.5 times 10 to the minus 5 to keep our significant figures there. In fact, to avoid rounding errors, we really should call this 12.5, and that might actually make a significant difference. Curious to see here, 0.015 squared times 0.005, 1.40. So it does change it a little bit. Hey, on Chem 21 labs, that would make a difference. All right, so that would be the value you'd probably want to use there, just based on the rounding errors going from this to that. Okay, so so that's the answer there. And then at the instant when NO is reacting at this rate, what is the rate at which O2 is reacting and NO2 is forming? Okay, so when NO is at this rate, all right, it's being consumed at this rate. The O2 is being consumed at half of that rate. Okay, so half as quickly, and so you would just divide that by 2, and you'd have 5.0 times 10 to the minus 5. All right, that would be the rate when at which O2 is reacting, and then NO2 is forming at that same rate. Okay, so again, that gets back to what I was talking about here, where we're looking specifically in this part of the question at the concentration, or rather at the rates of appearance or disappearance of each of these specifically, as opposed to the overall reaction rate. Okay.